I think we'll move on. I see Dan, you are online. Is Dan going to be running remotely, or are you running from here?
I can do it either way. Which way would you like me to do it? I can share my screen.
Yeah, if you can run it remotely, that would be great.
Yeah, go ahead and take charge remotely, Dan.
Okay.
Dr. Hodyss.
Okay. Can everyone see my screen?
Yeah, it looks fine here.
Okay, good. Good morning, everyone. I am Dan Hodyss. I work in the Remote Sensing Division with Dave Poole, and we are designing the next generation of ionospheric data assimilation for the Navy. So whenever you're looking at a new system, I think that there's two things you should look at. So one, of course, you should look at the statistics of the fluid you're trying to predict, and the other one is you need to figure out what the trajectory of your model is most sensitive to, because obviously you want to do data assimilation on the thing that has the strongest bang for your buck. And so that's the thing we looked at. So we looked at a variety of statistics for the ionosphere, and one interesting thing that came out was very long distance ionospheric correlations, which I'm going to talk about in a minute, and also this feature that the model trajectory is only weakly sensitive to the initial condition, which is, of course, the standard thing that the data assimilation is sensitive, is meant to produce, which is the initial condition. It is, in fact, more sensitive, at least in our model, the SAMI-3 model I'll discuss in a minute, to parameters and external forcing, so solar and mesospheric thermospheric forcing. And that's really what this talk is going to be about, the things that we saw that were most interesting to us when we moved from the troposphere to the ionosphere. So as I said, we're going to use this model called SAMI-3. SAMI-3 is the Navy's ionospheric model. SAMI-3 is a full physics Navier-Stokes solver. It simulates the transport and chemistry of 7 ion species. And it does so on a grid aligned along the geomagnetic field lines. We're going to see that come up multiple times in this talk. And so those people with tropospheric backgrounds and neutral forecasting backgrounds kind of think of the geomagnetic field lines in SAMI-3 as something like a vertical coordinate. And so we're always thinking on the geomagnetic field lines. So the version that we're going to use in the data assimilation experiments that we're moving towards right now is this version of SAMI-3 that's forced by a statistical empirical neutral model. So that uses this thing which we refer to as MSIS, and the horizontal wind model we refer to as HWM. And an example simulation of the SAMI-3 ionosphere forced by this statistical thermosphere is here. This is the 200-kilometer altitude level, and it's the electron density field. And it's, you can see the sun moving across the Earth and ionizing the electrons, giving us this electron density field here. Now, the future, though, where we're intending to go in the next step after we have an ionospheric data assimilation set up in JEDI for this model, then we will have this one, which is SAMI-3 being forced not by a statistical model, but by a full physics Navier-Stokes based solver for basically from the surface of the Earth up to 500, 600 kilometers. And you can see there are definite differences when you force a model with a smooth statistical climatological representation of the thermosphere versus one with rapidly evolving gravity wave radiation from below. So that's our model. And with that said, let me talk about some long distance correlations. So I'm interested in long distance correlations because ensemble data assimilation, at least in the troposphere and all the development that went on down there, is really predicated on a local assumption. There is a piece of the algorithm called localization, and it assumes things are local. And so we were very surprised to see so many very long distance correlations in the ionosphere. And this is a summary of some of the ways that we see long distance correlations in the ionosphere. So one type is we're calling a long field line correlations. And we see this in basically the motion field, in quotes, the winds in the ionosphere. So the ion and electron motions, this is the east-west electron motion. In a cross-section, this is a latitude-altitude cross-section up to 20,000 kilometers, and the cross-section is along a magnetic meridian. These curves here are field lines, and what you see is if we correlate the east-west electron motion at 100 kilometers here with the field in this plane, you see that along this field line, the correlation is basically 1. So the correlation doesn't go down. It actually remains constant along this field line all the way to the other side of the world and out 17,000 kilometers. So again, standard distance dependent localization doesn't really make sense in that setup. Another way you can see these field lines is not in the east-west, not in the motion field, so the winds in the model, but in the total electron content, and referring to this kind of correlation as a conjugate point correlation. So if you look in the total electron content and you now do a geographic meridian, right here, that's this latitude, and you correlate 20 north with the variables along that meridian, you will see that there's a peak, of course, at the location you're correlating, but there's also another one in the southern hemisphere if you do the northern hemisphere. And again, this is another long distance correlation. It's not spurious, it's real. And this one is also related to field lines. So both of these can be thought of as owing their existence to the fact that the ionosphere is highly constrained by the geomagnetic field lines. But there are other correlations which are very long in space that have nothing to do with the field lines. There is an across field line type of correlation, which you can also see in TEC, where this axis now is longitude, which is denoted in terms of relative local time. And so this is, say, the point we're correlating, and 12 hours would be the other side of the world. And so think of this as along the equator, along a magnetic equator at the center of the Earth. But through the ionosphere, and we correlate that, and you get this black line, which you see looks like a standard Gaussian at first, but in a standard Gaussian would have gone to 0 here. This never does. It flattens out. And these long distance correlations are due to kind of solar parameters in the model like F10.7, which drive a number of processes as we'll talk about in a minute. But all these long distance correlations have various effects on your data simulation. And so let's look at a few single ob increments just to get a handle for how you can see long distance correlations in single ob increments. So in these plots, we're looking at a single ob increment for a synthetic TEC observation and trying to update electron density. So let's start with this plot right here. In this plot here, we have another cross section along a magnetic meridian, the latitude, altitude, but this time we're only going to 1,000 kilometers. In the previous slide, we went to 20,000 kilometers. We're just focusing a little bit lower now. Here I am, while a TEC observation doesn't have an altitude, I wanted to denote the location of the TEC observation on this plot somehow. So what I did was, just for picture purposes, so we can all get a handle, I put the TEC observation at, in quotes, at the HMF2, which is 300 kilometers. So this is the height of the F2 layer. Just so we can get a look at it. Just keep in mind, of course, the TEC observation has no altitude associated with it, but this is the location of the point where we calculated the TEC right here. And so we calculate the correlation here between TEC and the electron density field, and you see this basically big broad area of correlation. The whole area is correlated, and correlated quite strongly. And if we look at the covariance, which is the actual single ob increment, right? The covariance is really, for a single ob increment, is basically all the structure. you can see that the tech here is correlated with a broad area throughout this meridional cross-section in the covariance. And if we look along this field line, so again, the equivalent of looking along a model layer, you can see right here that it's positive up here near where the observation is. Then it actually goes negative, the correlation between tech and electron density, way, way up at the top wherever this model, this field line goes. And then it comes back down and it's positive again on the far side of the Earth. And the increment looks like this. So along the field line, the increment is a spike here at minus 60 and another spike at plus 60. So if you did the standard thing, which is put a Gaspari cone around this and localize your increment, you would cut off this real part of the increment, which I don't think one would want to do. So another example of a single ob increment is now we're going to use the total electron content observation to update the ion motions in the model, in the SAMI3 model. And so this ion motion, which we refer to as U1P, is the motion in this plane, but orthogonal to the field lines. So in a sense, in a meteorological sense, you would refer this as kind of the vertical wind, because it's orthogonal to the layer you're looking at, or the level you're looking at. And so here, this tech observation is the easiest to see is along the field line. So let's look along this field line again. And you can see that the correlation between the total electron content ob and our update of the motion, the ion motions, is actually a constant there. It's just a total constant. It never changes on that field line. And the covariance, which is the single ob increment, has no real local structure to it. Again, if you put a Gaspari cone right here where the observation is, you would cut off the largest component of the increment. And the ion motions are a lot like the winds in a neutral model, in the sense that there is a balance that they satisfy. And so if you cut off these increments, you will be messing with the balances in the model, right? These ion motions satisfy something called the potential equation, which is an elliptic equation for the electrostatic potential, and it is forced by the electron density. So there is a specific relationship that exists between these motions and the electron density, which you want to preserve, and which you won't if you haphazardly do localization in your data assimilation system. So why does all this happen? Well, there's three things that we've seen that looks like they control the long distance correlations in the ionosphere that we see. So one is just solar forcing. Both the production of electrons and the recombination loss of ions and electrons are both functions of F10.7, and F10.7 induces this kind of global correlation around the globe through both production and recombination. And I'll give an example of that later in the talk. I mentioned these long distance correlations along the geomagnetic field lines. We explicitly make an assumption in the model that there is a high conductivity along the field lines, and that assumption leads to the electrostatic potential being constant on field lines, and that immediately implies long distance correlations in these ion motions that we just saw. And then there's, of course, the neutral winds and the composition. Those things come in through the electrostatic potential and force all sorts of things in the model. And if we use the climatological model, HWMMSys, those have really large correlation length scales. And so those push on the model to have very large correlation length scales. We have done the same kind of statistical calculations with NavGem and WACMX. And while we do see shorter correlations, they're still pretty long by tropospheric NWP standards. But one thing that deserves to be mentioned, I think, is that no matter what model you choose for the neutrals, the high parallel conductivity assumption is always going to keep very long distance correlations between the electron density, and the ion motion fields. That will never go away. So that's what I want to talk about in terms of long distance correlations. Now we're going to switch gears and talk about prediction and data assimilation. So I think a good way to think about the ionosphere is to imagine how it emerges each day in the morning from the neutrals as the sun shines on the Earth, and then it grows throughout the day, and then largely just condenses right back into the neutrals each evening. And so this means that the initial condition is not going to be at least highly constraining, or at least damped, after about 24 hours. And we argue in a recent paper that we have in Journal of Space Weather and Space Climate, that this is even shorter, because things should actually be at the recombination time. Also leads to a damping of information and a loss of information from the data assimilation to the initial condition. So since data assimilation is all about the initial condition, what can we do? Well, what we need to do is think about what things really control the evolution of the ionosphere. And I think that a really powerful part is the external forcing, i.e. the thermosphere, the mesosphere, the neutral part of the atmosphere, and then parameters. And by parameters, I mean solar properties, because in the SAMI3 model, we bring in the sun, we bring all that solar forcing in through various parameters. And so data assimilation really needs to be about those guys. So to that end, we developed an ensemble Kalman filter using SAMI3, and we did it outside of JEDI as a model. And the model was to kind of help us understand where we want to go within JEDI. And so this is kind of the idea that we have of where we're trying to take the JEDI implementation. Right now, this setup has a variety of features, and we've come to some conclusions about what is necessary and what isn't necessary. So the system that we did develop can be run as an ensemble Kalman filter or as a quadratic polynomial filter. The quadratic polynomial filter explicitly allows you to account for skewness in the ensemble distributions. We tried that, and we didn't see much difference. So I think that's saying there's not much non-Gaussianity in at least the experiments we tried to look for non-Gaussianity in the ionosphere. We ran the system as either deterministic in the form of an ETKF for ensemble generation, or as stochastic. Again, we tried both, and honestly, we didn't see too much difference. So we decided to stick just with ETKF. And the setup that we did the experiments with makes use of an ASSI setup with observations of just total electron content. And what we did, and I'll talk about a little bit more later, is we used a stochastic model for the F10.7 time evolution. And that was because the F10.7 we had available was at a daily rate. And really, we wanted to do data assimilation at a 1 hour rate for the F10.7, and we wanted a known truth that we could deal with. So we generated a stochastic model that created a F10.7 times evolution that followed the Earth's true one, but did so in a Brownian motion. So we update, the data assimilation system updates all the state variables in SAMI3, so that's 7 ion densities, E cross B drifts, temperatures, electrostatic potential, and some parameters. And the version of SAMI3 that we used here, again, is this climatological neutral model. And of course, right, the idea here is we want to update F10.7. So you got to look at the correlation between your observations. We said we were going to use total electron content observations here in this test. And we need to correlate those with F10.7. So we did that here. Here, these circles here on the plot are solar zenith angle. And so this central circle denotes that the sun is directly overhead, right at the central circle. And if you look at each one of these, you can see these are at different times. Basically, this is at 0Z, 6Z, 12Z, and 18Z. And you see that there's a positive correlation during the daytime, and there's this interesting negative correlation at night. So large F10.7 values actually enhance your recombination rates, and then you get more damping at night, which is kind of an interesting result. So this means, yes, definitely tech observations have a lot of information about F10.7. So we can do assimilation for F10.7 values. And so in this top panel, the black dots are the true F10.7 values for the first 6 days of January 2014. That's what we're looking at. Green is this Brownian motion model I mentioned earlier that follows the true value, but does so with a Brownian motion. And so we're going to simulate, we're going to run SAMI3 with those F10.7 values, changing with time, and call that truth. We'll sample tech observations from that, and then we'll send off our ensemble Kalman filter to do data simulation on those tech observations. And for example, this red curve is the posterior, or the analysis we get of F10.7. And so you can see it follows the true F10.7 values with an hourly assimilation rate very well. But what I want to draw your eye to is a point like this right here, where it changed from day 3 to day 4. And you see the truth and the analysis, and the analysis is lagging the truth. And that happens on multiple days. That seems to be a standard thing that happens in the data simulation for parameter estimation, that you get these time lags in the assimilation, which leads to an error. These curves here are the errors in F10.7. And then if you look here, this is the error in the tech. And you can see that the error in the tech is phase lag. It's later than the actual error in the F10.7. And that's because the actual electron density takes time to react to the F10.7. And so that's why I like to say that the data simulation of the ionosphere is a tale of time lags, where you get this time lag in the DA, and you get a time lag in the response of the electron density to the changes in F10.7. And then you get also, there are time lags between changes in the neutrals and changes in the ionosphere.
1 minute, Dan.
Got it. Conclusion. So we have, so what we saw long distance correlations, and to me that implies long distance increments, but I think that requires a serious rethinking of modern localization techniques. We've been working on those techniques. In the meantime, we're going to build an unlocalized ensemble-based data assimilation system for the version of SAMI3 that we have, and the main feature will be parameter restoration for both solar forcing as well as thermospheric parameters in HWN emphasis. Thank you.
Yeah, thank you very much, Dan. We're a little over time. Maybe one quick question, or we can save it. Yeah, go ahead.
Yeah, there seemed to be a little bit of mixing between correlations that you were drawing out of data earlier with the TEC, and then correlations that you're drawing out of the ensemble runs of the SAMI3. So I think that the conclusions you're drawing are primarily about this ensemble of runs that you did with SAMI3, and you're drawing conclusions about long distance correlations from that. If that's not the case, can you expound a little on how you differentiate those?
So if you're talking about the slide with the 3 types of long distance correlations, this is true whether you do climatological correlations or you do ensemble correlations. Is that the answer to your question?
So I can't see the slide you're referring to. No. I
mean, it's not sharing anymore? Oh, sorry.
But effectively, you were, towards the end, you were saying that, you can see it, maybe I can't see it, that you're drawing some of these conclusions about how you're going to do data assimilation. Some of those things, like your long field line plasma motion, I don't really see how you're drawing that from data. If you are, that's what I'm interested in. That's something that I think you're drawing out of the...
No, I'm not saying anything about, I mean, I don't know what the true correlations are. I have SAMI3 and I'm looking in SAMI3. And in ensemble data assimilation, you have a model and it's telling you what the correlations are.
Correct. And so in your long distance correlation slide, there were 3 elements you went over. One of them was along field line plasma motion. So that was an outcome of the SAMI-3 model.
Yes, all
Not
these correlations
data.
are from models. I don't have data for those things. Yes, exactly. Right, I want to
Yeah.
learn about these correlations from the model because I don't have any other way of learning about it.
Yeah, thank you. And we'll have to move on here in the interest of time. And yeah, Dave Cool here is local. You can definitely pick his brain and he can be a conduit to Dan. So Nick Dietrich is gonna wow us with a presentation on specifying the upper atmosphere through data assimilation of radio occultation observations. There we